Okay, this is a acceleration uh, lecture. So we'll be covering how things speed up and change, speed and direction. Um, okay. So these are six of the kinematic variables that you really should know before going into this. Um, Position, or x, is a separation between an object and the origin. Distance, or d, is the total length an object has traveled. Displacement, or delta x, is the change in position. Instantaneous speed, or s, is the rate which distance is traveled at any given moment. And the moment part there is very important. That's why it's bold. Average speed, or s average, is the total distance over time. It's the speed over a long duration. And lastly, velocity is speed with direction. Okay, changing velocities is a very common thing that we'll be seeing very often within our physics coming up here. Just everyday moving around and things causes so many changes of velocity that we really need to be able to define it. However, before we do, a velocity, when it changes, we need to be able to describe different velocities within a problem. So we're going to introduce two new velocities. Initial velocity, or VI, is how we will represent the velocity at the beginning of a problem or time interval. Initials, just like if you were to be asked to write your initials on a paper, is the very beginning of your name, and this is the beginning of the problem. Final velocity is, or VF, is the velocity at the end of a problem. Sometimes in a problem, and we'll also see that the variables are given in words. Be very vigilant for the phrases stopped or at rest. These will indicate that the velocity is zero at some point in the problem. Usually at rest means that the VI is zero, and stopped means that the VF is zero. Although that is not a rule, it's just you see it it's the most frequent way you see those things. But please make sure you do think about those things in the context of the problem. Acceleration is defined as the rate which velocity changes over time. Represented by the letter A. When we measure this, it should be measured in meters per second squared, or m over s to the second power. An equation for finding acceleration, the definition for it is A equals Vf minus Vi over t. Acceleration really is just how much your velocity changes every second. If you have an object that's initially stopped, an acceleration of 2 meters per second squared means that the velocity will go up by 2 every second. So at 0 seconds, we're traveling at 0 meters per second. At 1 second, we're traveling at 2 meters per second. At 2 seconds, we're traveling at 4 meters per second, and so forth. All right. The last detail about acceleration is that the direction of it really matters. When we see an acceleration in the same direction of an object's motion, we're going to see that car or that object speed up. So in this little blue car, we can have so going forwards, the person steps on the accelerator pedal, the car is going to begin to speed up. An acceleration in the opposite direction of the car's motion results in a slowing down. So if you have a car that's moving forward and the driver steps on the brake pedal, the car will slow down. That's really important to watch for, and negative signs in the problems are very important to make sure you include them. Okay, so we're going to look at a few sample problems here just to make sure we know what's going on. So our first one is this acceleration problem. Okay, we have a car that's accelerating from rest at 26.8 meters per second over 6 seconds. What is the acceleration? When you're solving a problem, it's really important to write down your knowns before you start doing anything. So in this case, I see the car starts from rest. Rest indicates that the object is starting the problem traveling at 0 meters per second. So we know our VI is 0. The problem also indicates that our car eventually speeds up to the speed of 26.8 meters per second. Since I can tell here that it's going from 0 to 26.8, it's really, those context clues are really how I'm able to tell what my VI and VF are. In addition, the problem tells me that the time that the object is traveling and speeding up is 6 seconds. Alright, from there, it then asks us to solve for acceleration. Alright, so we're going to look at our acceleration equation, which is A equals Vf minus Vi all over t. Okay, we'll plug in. Our acceleration stays the same because we do not know it. Our Vf is 26.8. Our Vi is 0. T is 6. So from here, we're going to take A equals, and this simplifies to 26.8 over 6. So with a very quick calculation, we should see that our answer is very easy to get. And we should find that our answer here is about 4.47 meters per second squared. There we go. So there is our solution. Let's look at our next example real quickly. Okay, a car traveling 18 meters per second brakes to stop at a red light. The car accelerates at -5 meters per second squared. How long does the car take to stop? Okay, let's see what we can do. Alright, so looking at our knowns once again, it tells us the car is traveling at 18 meters per second before anything happens. So I can tell by the units and context that the VI of this problem is 28 meters per second. Okay, then the car begins to brake for a stop. The stop is a key word here, and we can kind of see that after the braking happens, we're at 0 meters per second. So that's a pretty clear indication that is our VF. It tells us the car accelerates at a rate of -5 meters per second squared. This negative is very important because it does indicate we're slowing down, which does match up to what the problem is asking us to look at. So that's something we want to really make sure we're showing here. And then it asks us, lastly, how long does the car take to stop? Okay, looking at our equation now, our definition is A equals Vf minus Vi all over t. So if we plug in, we know our acceleration is -5, Vf is 0, 28 is Vi, and t is unknown. So to start things off, we're going to simplify a little bit first. So we get -28 over t. And we know from our algebra skills that we need to multiply both sides by t to get it out of the denominator. That'll cancel, and we get -5t equals -28. Okay, to solve this thing out then, we divide both sides by -5. And we find that t is equal to 5.6. seconds. Okay, and that is our final answer. Let's look at another slide yet, and then we'll move on to some different problems. Okay, these are our 3 kinematic equations. With these equations, we are going to be able to solve a lot of situations that involve constant acceleration. All right, we're going to simply choose one of the equations when we're working with a problem, and it'll kind of best determine that will be determined by what knowns we have. Let's look at an example. I'm going to do number 5 on the attached worksheet to the notes. Okay, here is number 5. How far would a car go if started from rest and accelerated at a rate of 9 meters per second squared for 6 seconds? All right, let's kind of pull this apart and see if we can find how far it would go. All right, so looking at our equations we have up here and what knowns we know, we'll be able to do this fairly quickly. Okay, number 5 asks us how far will the car go. That tells me right away that we are looking for delta x. Okay, you should always think how far means that the delta x is missing. All right, from there it tells us the car started from rest. So once again, we should understand our VI is 0. Because if it starts at rest, it means that it's not moving at the beginning of the problem, which means VI is 0. And it accelerates at a rate of 9 meters per second squared, so it tells us what the A is, 9 meters per second squared. That unit there indicating once again that it is an acceleration. And then it tells us that it does so over the course of 6 seconds. Looking at our equations here then, we can see that they have different variables in them. The one we want to choose is the equation that has the 4 variables that we have right here. So looking up here, this one has delta x, it has VI, it has a t, it has an A, it has a t. So that one's going to be the one we want to choose. If you notice, the other ones here have VFs. VFs we don't know, and we're not looking for it, so that's not an equation we can actually use in this situation. So from there, we're going to copy down our equation again, just to kind of give us a bit of a starting point. And now we begin to plug in. Okay, delta x we don't know, so we leave that one go. VI is 0, so that is 0. T is 6. 1/2 9 times 6 squared. Try to be careful when you are plugging into your equation, because it's surprising how often you do see people mess that up. And at this point, because delta x is already by itself on that side of the board over there, we can solve just by typing directly into a calculator. So if you type in what we have up here into a calculator, you should find that the delta x in this situation is 162 meters as a final answer. Okay, we're going to look at one more question and then I'll kind of set you guys free. So we are now going to look at number 8. Okay, number 8 asks, a cyclist starts from rest at the top of a hill. She begins to descend the hill. After 20 seconds, she reaches the bottom of the hill, traveling at a speed of 50 meters per second. How far did she travel? Okay, let's start pulling this one apart, see if we can get an answer. Okay, number 8. It tells us the cyclist starts from rest at the top of the hill. Once again, this is going to be a situation where our VI is 0 because of the at rest phrase. Okay, she begins to descend the hill after 20 seconds. That means our T is 20 seconds. She reaches the bottom of the hill traveling at a speed of 15 meters per second. I can tell that this is our velocity, our final velocity, because of the fact how it's written. And it then asks us once again, how far? So that is going to be asking for us to solve for delta x. Okay, from here, let's look at our equation, see if we can find one that has all 4. Here in our first equation, there's an acceleration. We don't have that, and we do not know that. So we are not going to be using that equation. But here we have delta x, VI, right, there's VI, VF, and a T. This is the equation we want to use for this problem. So let's write it out, and then we'll plug in. Delta x equals 1/2 vi plus vf times t. Okay.